Hello, everyone. Welcome to this webinar series number 4 in our mobile mapping webinars. My name is Bishoy Gerges, and I'm today here with my colleague, Carl Chow, and we will be presenting to you episode number 4 regarding POSPac processing. It will be great if everybody can hear me well. Would send something like, hey, we hear you, or we don't see screen, or if you have any problems, please send us on the chat. Okay. So, thank you again. So in this webinar series, I would just like to do a recap on the previous episodes that we have been through. So in the beginning, we did a general introduction on this series, and after that, we had follow-up on the factors influencing the accuracy of your mobile mapping data. We learned about the best practice, and we learned about the different factors that could affect your data. And then our final and last series was about the point cloud registration in TBC that was presented by my colleague Miguel. And in this episode, we will present to you how to get the best out of your POSPac. To get the best out of your POSPac, we decided that we will split this into 2 parts. So in this first part that we're discussing today, we'll be focused more on the different processing modes. And in the second part, we will be mostly focusing on showing you how everything is done in POSPac, and in addition, other factors. So I think I will handle now the presentation to my colleague Carl, and I would like to remind you all that this is mainly, we're focused on the land mobile mapping products, and we will not be discussing other types of data that come from marine or aerial products. So thank you again, and Carl, please go ahead with the agenda.
Okay, thank you, Bishoy. So the agenda for today, first of all, we need to know why should we use POSPac. After that, I will introduce the general workflow of data post-processing, how to choose the best processing mode for your data set, depending on the situation. And then we will compare the results of different processing modes based on our own test. After summarizing, we will have some time to try to answer your questions. So please, if you have any questions during the presentation, feel free to send it to us by using the chat tool, and we will correct them and answer them together at the end.
Yeah, that's good.
So what is POSPac? Why should we use POSPac? POSPac means the position and orientation system post-processing package, mobile mapping suite. This is the post-processing software package for airborne, land and marine applications. The advantage of post-processing over the real-time solution is there are no broken data link from reference station or VRS, and with the post-processing, we can process the data in forward and backward as well to calculate the sensors. With infusion technology, POSPac will help to improve the accuracy and robustness of the trajectory. If you don't have POSPac, you can only use the raw post data, which means you cannot expect the accuracy, and the quality of the data will be pretty bad without GNSS corrections. What is infusion? So infusion technology is using used in POSPac to adjust the limitations of traditional high accuracy differential GNSS processing. So with the traditional solution, we need to close to a reference station, and we need to maintain the GNSS signal checking. With infusion, there are two main improvements from the traditional methods: the tightly coupled processing and the IAKAR, which we will explain right after. From these two graphics, we can see the difference of the standard loose coupled aided inertial navigation and the infusion tightly coupled processing. For standard loosely coupled aided inertial navigation, the GNSS receiver computes its solution independently from the Kalman filter. But for infusion tightly coupled processing, the observables are processed by the Kalman filter. The key difference here is that the Kalman filter processes the raw shooter range and carry phase observables directly from the GNSS receiver, thus bypassing the receiver's navigation filter. This means the system will be able to benefit from GNSS observables even there are less than 4 satellites. This is quite useful, especially for land mobile applications when the GNSS signal is often abstracted. With this simplified schematic, we can compare the traditional KAR and the infusion IAKAR. Traditionally, we use kinematic ambiguity resolution. The GNSS needs to compute its own position before it can help the INS, and it requires at least 4 satellites and some time to resolve the carrier phase ambiguities before it can compute a solution. Here we will face a problem where GNSS signal is obstructed. With infusion technology, not only the GNSS helps the INS, but also the INS position is used to help the GNSS to remember its position, even when checking 3 satellites or less. This allows much quicker ambiguity resolution after a complete outage, or allows keeping carrier space ambiguities fixed, even if there are less than 4 satellites. In general, the data processing workflow is straightforward, but there are some choices that we can use to make your project better or worse. The workflow is quite simple. You need to import the raw file, choose the proper rover antenna modes depending on the system you are using, set the level arm standard deviation, and then import the base station files if there are any available. In GNSS inertial processor, you need to choose the proper processing mode, then decide should we use DMI and GAMS, and select the proper initialization options. After that, we can generate the aspect file. At the end, we should view and control the quality by using display plots in POSPac. During this presentation, we will focus on how to choose the best processing mode depending on the situation. The other topics such as GAMS, DMI, and other options will be part of the next webinar. Now I will try to introduce the different processing modes and how to choose the best processing mode for your dataset. As you can see, there are many different processing modes in POSPac. We have infusion SmartBase, infusion single base or multi-single base, infusion PVP, and infusion autonomous. Here we don't discuss about PPRTX because it's currently not part of the Trimble imaging portfolio. Also, we won't discuss about the GNSS snake because it's a loosely coupled processing mode and it's not recommended for land mobile applications. So I will start from the first one, the infusion single base. What is single base? So it uses a single base to correct the GNSS pseudo ranges. It can use GPS, GLONASS, Beidou, Galileo, and QGIS satellites as well. From the graphic, we can see the base station location is known accurately, and then it receives the GNSS signals, calculates the pseudo ranges to the satellite, and determine the range error. After that, the base station will transmit the range corrections to the rover, either in real time or for post-processing. For example, in POSPac. So, and the rover station can receive the GIS signals, calculate the pseudo ranges, and then we apply the range corrections to determine the right position. When should we use the single base? So in case the whole mission is within 20 kilometers of a single base, this is optimal. Or the whole mission is within 70 kilometers of the base, and it's not possible to use SmartBase. If the baseline is more than, for example, more than 70 kilometers, so you should try maybe the PVP and compare the results. How to use single base? To use single base, we have two options. Option one, you can use your own base station data. To do this, you need to import the Linux or Trimble file, check the coordinates in the coordinate manager, or compute RTX coordinates, which we will introduce in the next slide. And then we can set it as base station. So as we said, so if you are unsure of the base station coordinates or reference frame, you can use these computer RTX coordinates. The second option to use single base is to use the Find Base Station tool in POSPac. Open the Find Base Station tool, select single base, and then the system will search the base station within the search radius. Using this option, you don't have to check the coordinates and the reference frame. Note that you can also add your own GIS server database. What can we expect from the single base processing mode? The positional accuracy depends on the baseline. For short baseline, within 30 kilometers, it's about 2 to 5 centimeters. And for long baseline, within 100 kilometers, the accuracy is less than 10 centimeters. Note that, so for short baseline, you should start the mission within 30 kilometers and don't go further than 30 kilometers from the base. And for the long baseline, you should start and stop your mission within 30 kilometers and don't go further than 100 kilometers from the base. This means you should try to start and stop your mission close to the base station. The error increases by about 1 millimeter per kilometer of the baseline. As we said, so try to start and stop the mission near to the base, and this will help to improve the data quality. Similar to the single base, we have another processing mode called multi-single base. So it uses various single bases to correct the GNS pseudo ranges. Each part of the trajectory is corrected by the nearest base. In other words, the nearest base is not always the same. It will be changed along the trajectory. Same as a single base, we can use GPS, GLONASS, SPADO, and UZSS satellites. When should we use the multi-single base? So in case there are more than one nearest base along the trajectory, and your mission is always within 20 kilometers of the nearest base, this is optimal for our mission. Or in other case, the base data doesn't meet SmartBase requirement. So in this case, we can use the multi-single base. This is typical for long linear projects, such as long highways, power line corridors, especially if the conditions are not good for SmartBase. So we can use the multi-single base. How to use multi-single base? So we need to select multiple base stations to create the multi-single base station. The system will automatically verify if the selected base stations will allow processing and then exclude those which are not within the processing criteria. So for example, if a base is never the nearest base for your trajectory for the whole mission, it will be excluded. Once it is finished, a new entity will appear in the project Explorer and called MTSBX, so multi-single base X. The positional accuracy depends on the baseline as well, same as the single base processing mode. So for short baseline within 30 kilometers, it's about 2 to 10 centimeters, and for a long baseline within 100 kilometers, it's less than 10 centimeters. So same as single base processing mode, for short baseline, you should start within 30 kilometers and don't go further than 30 kilometers from the base. And for the long baseline, you should start and stop your mission within 30 kilometers and don't go further than 100 kilometers from the base, which means you should start and stop the mission close to any one of your stations. Again, the error increases by 1 millimeter per kilometer of the baseline. So in Fusion SmartBase, what is SmartBase? It uses a network of base stations to correct the GNSS pseudo ranges. It looks like a virtual reference station concept, but optimized for mobile mapping applications. GNSS observables for each epoch of the mission will be calculated as if a reference station exists at the lowest location throughout the whole mission. We can use GPS and GLONASS satellites for this processing mode. When should we use SmartBase? So in case our mission is within a network of at least 4 base stations, and some parts of your mission are at more than 20 kilometers from your nearest base, as we can see from this graphic. So in this case, we can use the SmartBase processing mode. How to use SmartBase? First of all, we need to download the base stations and then run SmartBase quality check to see if the base stations are acceptable to be used to build up the network. This is optional. Optional. After that, we can run the Applanix SmartBase to process. To download the base station data, you can use the Find Base Station tool in POSPac. Select to use SmartBase in the lower left corner and change the search radius if needed. The system will automatically to check the data availability to download them. After post-processing, a network surrounding the trajectory will be created. Ideally, the trajectory should be completely inside the polygon. In addition to download the base station in POSPac, so you can also try to use your own base stations to, for example, to fill the gaps or to densify the network, or even you can create the whole network from scratch. This will need some specific requirements. So if the position area of the base station is known as less than 5 centimeters, you will need the base station data which cover 2 hours before your mission and then at least 5 minutes after your mission. If the position area of the base stations is unknown, so you will need at least 18 hours of continuous observation, free of data gaps and cycle slips for the SmartBase quality check. This is average out any multipass variations due to the changes in satellite positions. As we talked, so we can select a SmartBase quality check to perform a network adjustment of the base station coordinates. This is optional. In case the error is bigger than 5 centimeters, the base station will be indicated as bad position and its coordinate will be adjusted. If less than 18 hours of continuous observations, free of data gaps and cycle slips, the base station will be indicated as bad estimate and it will be disabled. After running SmartBase, so GNSS QC statistics will be displayed, and then a SmartBase region will be indicated in the plain view. What can we expect from the SmartBase processing mode? For short baseline within 70 kilometers, so the positional accuracy is about 2 to 10 centimeter, and for long baseline within 100 kilometers is about 10 to 15 centimeters. The entire mission should be within the smart network, and for short baseline, the rover should not extend further than 70 kilometers from the nearest base and should remain within the SmartBase network throughout the whole mission. And for long baseline, the rover should not extend further than 100 kilometers from the nearest base and spend at least a few minutes within 70 meters from a base. Infusion PPP. So PPP means precise point positioning. It uses a network of GNSS reference stations distributed worldwide to provide precise satellite orbit and clock corrections. This is worldwide and no need for reference stations, but requires a long initialization time for about 30 minutes of gap-free. So it should be in good GIS conditions. PPP is limited to GPS satellites only. When to use PPP? Only when there's no reference station available within 70 kilometers of your mission, and it's not possible to use SmartBase. So PPP only effective where the GNSS coverage is uninterrupted. So this means we always recommend to rely on base stations, but if for any reasons the base station data is unavailable for after the mission, then you can switch to PPP. But so you should aware of the limitations of PPP. So it will take about 30 minutes of uninterrupted GNSS signal before it can coverage to its optimal precision. How to use PPP? So simply import raw data, and in the GNSS inertia processor, select Infusion PPP to run the processing. You need to accept the PPP download and select the express mode. The expected positional accuracy for PPP is about 10 to 50 centimeters. And again, so make a long static initialization for about 30 minutes in area with good GNSS conditions. Next one is the autonomous. Autonomous relies solely on the navigation devices and the ephemeris. When should we use autonomous? Only when none of the previous processing mode work. So autonomous is not recommended to be used. We normally use it for support purpose to troubleshoot issue. To use Infusion autonomous, import the rover files and select Infusion autonomous in the GNSS inertia processor. You can run the processing. The positional accuracy for CA is about a few meters, and for DGPS is about few centimeters to few decimeters, depending on the corrections resources. The trajectory is not smooth and it will be bumpy, depends on the situation. of your mission. So this is all the processing mode we will introduce, and after introducing all the different processing mode, I will compare the result from different processing modes that we tested based on the dataset we got from our customer ESP. The goal for this comparison is to calculate and compare the relative accuracy of different processing modes. The method we use is to measure the relative distance between multiple targets, which we can see from the multiple passes. We are not using GPS here, as we don't want to be influenced by any error from the GCPS. So we only compare the relative accuracy. In this test, both the GAMS and the DMI are disabled. And we compare the measured precision against the predicted precision from POSPac user guide and with against the calculated precision from the aspect RMS. Here is the whole trajectory and the location of our target. With this picture, maybe you can clearly see the location of the target. So they located on the roadside along our trajectory. This is an example of our target. It's a reflective rectangle on the pavement. The measuring method we use is we locate the center of each target hit, and then we measure the distance between each hit and the average hits, and the average hit location for this target. So we calculate the standard deviation, which gives us the estimation of the relative accuracy. Again, the relative precision is not measured between the hits and the GCPS, but between the hits and the average of the hits precision for each target. We repeat this process for each processing mode. As we said, so we compared the measured standard deviation with calculated error RMS. To get the error RMS, we can go to the display plots. Under view statistics, we can get the calculate error RMS. So now we can show our result of the comparison. From these graphics, we can see the RMS, the error RMS of the single base processing mode with short baseline. So you can see the baseline is about 5 kilometers. It's very close to our mission area. So for the most areas, the north and east position error is within 1 centimeter, and the down position error is about 2 centimeters. We can compare the measured standard deviation with the expected accuracy from the POSPac user guide and the calculated error RMS values. So the expected accuracy for single base with short baseline is about 2 to 5 centimeters. And the calculated error RMS for north and east is about 1 centimeter, and for down position is 1.4 centimeters. Based on our test, the measured standard deviation for X and Y is a few millimeters, and for Z is about 1.5 centimeter. The general standard deviation is about 1.8 centimeter and maximum 3.5 centimeters. So you can see from the graphics, so on the right side, all the target hits are overlapped very well. So for single base processing mode with long baseline, for most areas, the north and east position error is within 1.5 centimeter, and the down position error is within 2.5 centimeters. The expected accuracy for single base with long baseline is less than 10 centimeter, and the calculated error RMS of north and east position is 1.3 centimeters, and for down position is 1.8 centimeters. So you can see almost the same we got from our measured standard deviation. So for X and Y is about 1 centimeter, and Z 1.7 centimeter. Generally, the standard deviation is 2.3 centimeters and maximum 4.6 centimeters. For SmartBase with short baseline, for most areas, the north and east position error RMS is within 1.5 centimeters, and the down position error RMS is about 2 centimeters. Here we can see the difference, and the expected accuracy is 2 to 10 centimeter, and the calculated error RMS is almost the same as our measured standard deviation. So for X and Y, it's about within 1 centimeter, and for Z, the deduction is about 1.4 centimeters, and generally the standard deviation is about 1.7 centimeters. So we can see from the graphic right side, so all the target hits looks quite good and overlapped quite well. For long baseline SmartBase, so the north and east position error RMS is within 2 centimeter, and the down position is about 2 to 2.5 centimeters. With the expected 10 to 15 centimeters accuracy, after the calculated error RMS and the measured standard deviation, we got about 1 centimeter in XY deduction and 1.6 in Z deduction, and the general standard deviation 2.1 centimeters. You can see all the target hits are overlapped a bit less than the others, but it's very good. For PPP, the north and east position error is within 25 centimeters, and down position error RMS about 35 centimeters. With the expected accuracy of 10 to 50 centimeter, so we get a bit different compared to the calculated error RMS and the measured standard deviation. So for the error RMS, the north and east is about within 20 centimeters, but the standard deviation for X deduction is about 40 centimeters. And the general standard deviation is 45 centimeter and maximum more than 90 centimeters. We can see from the right side, all the target hits are not well overlapped. For autonomous, the position error RMS is a few meters, and same we expect the accuracy is a few meters. Based on our measured standard deviation, looks quite better than the calculated error RMS, but it still reaches 60 centimeters in general. We also test the real-time solution. So as you can see, the error RMS looks unstable and reaches a few meters. The measured standard deviation is about 2.4 meters. We can see from the trajectory on the right side. So these are hits from the same target. So the pink lines are the real-time trajectory, and the green lines are the calculated trajectory in POSPac. We can see that the relative precision of real-time solution is very low. Also, we can see here from this graphic, so for the same target, they are totally way off. Here is an overview of all these processing modes. In general, most of the processing modes are within our expectations. So expect the PPP. So you can see the PPP is a bit out of the expected accuracy. This may be because of the GNSS is abstracted. Some of the processing modes are even better than expected. So for example, the SmartBase and the single base short baseline and autonomous as well. So especially the SmartBase, you can see the accuracy is quite good, and this is might because of the good network polygon of our network. Also today we learned about how to use POSPac to improve the accuracy of the data. We learned that infusion technology is useful for land mobile systems. We need to choose the proper processing mode based on the base station availability and the shape of the trajectory as well. Infusion tightly coupled processing mode are recommended for our land mobile systems. So based on this, single base or multi-single base and the SmartBase are recommended than the PPP and autonomous. Even we don't have POSPac, we can still use the real-time raw data, but we cannot expect the accuracy. It will be unstable, depends on the environment. Here are some reference you can use. So the first one is the POSPac GIS Inertia Tools User Manual. So generally, you can find everything for POSPac post-processing in this manual. And you can also see the post-LV installation and operation guides. The third one is an article about the infusion technology. You can have a look on it. Next time, we will introduce the second part of getting the best out of POSPac. It will involve the GAMS, DMI, initialization options, and put our hands on the software. This is scheduled for October 15th. So now is the time for questions. If you still have new questions, you can send it to us by using the chat tool. Or if you have any questions after the webinar, please feel free to contact us by sending an email to imagingspot@trimble.com. Thank you. So Joy?
All right. Thank you, Carl, for the presentation, and we will be taking your questions now. So I have a couple of questions that I have received during the presentation, and please feel free to send anything via the chat or the question. All right, so we have a question here asking how many base stations I need for SmartBase method. So for the SmartBase, you will need at least 4 base stations, and it can handle up to 50. We have another question asking, after processing, I need to export latitude, longitude, height with GPS seconds and weeks. I cannot export to GPS seconds. So this is a bit out of the scope of the presentation, but we'll be discussing similar tools in the next webinar. But for the sake of answering this question, you can simply use something called the profile manager. And in the profile manager, you could basically design your own format that you would like to export. And from that format, you could choose what time format you would like to have with your entry. And in the time format, there are so many time formats, and I've just checked at the moment, and I could see everything that you're asking for. So please look for the profile manager, and if you own POSPac already, you could look on this in the manual. All right. A question saying, am I right if I process with GAMS and DMI, the solution will be the best solution to process the data? So we will not go through processing with GAMS and DMI now, as we explained. So this is this webinar is only about choosing the best processing modes from the different infusion, single base, multi-single, or smart. In the next webinar, we will be going into details on using GAMS and DMI. Also, we've explained in a previous episode of the series how can the GAMS and DMI both influence and affect your data. So both together could give you an idea on when to use or when not to use GAMS or DMI. Okay. So another question asking, can we export the TRJ file from POSPac? I'm not actually sure about what is a TRJ file format, but as I mentioned before, POSPac offers lots of possibilities to export your data, either in the sbit.out binary format, or you could export as KML. You can also use this profile manager to export in your own customized format. Okay, we have a question now. Is it available to use different datums and georeads? Not sure what you mean exactly using different datums and georeads. If you mean by exporting your data or setting different datum georead for your base station. So maybe you could just write me again on this one. Certain datum for base station. In the profile manager, in the coordinate manager of your base, as explained by Carl, you could set your base coordinates properly, and you could use the reference frame of your base. The question here coming from what POSPac did you use for the test? So for that test, we used AP40. All right, so we still have 9 more minutes, so feel free to ask anything you would like. Okay, so one last question coming here, or 2 more. Okay. Is it right single base is better than multi-single base? Well, the whole point of this presentation is that we show you the different processing modes, so you could choose based on your data shape, based on your area. We cannot tell you now what is better. There is no better or worse. There's just a better for different scenarios. So I cannot tell you. This is the whole point here is that we want you to choose the best based on your trajectory. So we cannot say what is best or not. Question: any idea where SmartBase download is available? So there is a service that that Applanix is connected to. So your POSPac is connected to the default service that downloads available base stations. And this is just simply the button that is called Find Base Station in POSPac. If you would click the button as was shown in the presentation, you'll get a list of all the available smart bases that you could, base stations that you could download. You could also, of course, add your own base station as was explained before, and you can also add your own base stations database. So POSPac could look into that and download base stations. Okay, so it means geographically available in default. So it checks the publicly available data based on the services that are Applanix, the POSPac is looking for. So there is no like what is default or not default, but it checks what is available around your area. And in some areas, the available base stations or publicly available in the POSPac service is a lot. So you must find like 20, 30 base stations near your trajectory by default included in the find base option, or you might find none. And in that case, you might need to go and choose a different processing mode. All right. So I think one more question. If I have subscription to Trimble VRS Now, can I set up SmartBase to connect directly to the available VRS Now base stations? This is a good question. I'm not sure if this could be done because the VRS Now is web-based and it's not for Atlantic to connect to a service or to the database of base stations. It does not use actually a website. It needs to be an FTP, as I see from the manual. So I am not 100% sure if you can do it. So I think I will take this question and then I will try to send you an answer later. So I have your name and email here, and I will send you an answer. What is the last POSPac version that can use SmartBase? Not sure what the last mean, but the last available POSPac is we have 8.4 with the service pack, and SmartBase has been working basically since I've seen POSPac. So I don't know, for maybe 3 years now. I don't know what was the oldest one. Could you also send me information about connecting to VRS Now? So VRS, yeah, sure, of course. All right. Okay, so I think we are through our presentation, and I think it's time now. So thank you everyone for attending this, and we hope you enjoyed it. We hope it was informative to you. So as usual, you'll get an email after the presentation. Usually you'll get this email tomorrow with the recording. So you could review the recording, and if you have any questions, please do not hesitate to contact us on imaging support. Thank you again, and wish you a good rest of the day or evening, depending on when you are, and hope to see you in the next webinar.